Hello everyone, today we are going to do differentials. Now last time when we were talking about Newton's method, we used tangent line to find the zeros of the function. In here, we will see how to use tangent line in another form. Now remember, the tangent line to the graph of the function at the point C and f of c is given by this equation y equals f of c plus f prime of c times x minus c. We're going to use this tangent line as an approximation of the graph of the function f. Now let's look at the picture or the graph below. Now, remember, the tangent line to the graph is given by what? Y equals f of c plus f prime of c times x minus c. Now this x minus c is called the change in x. Here, this is the x minus c we are talking about, and we denote this as delta x. This is the change we're talking about, this delta x. And when this delta x is very small, the change in y is represented by delta y. So this one is the change in y. So when delta x is very small, delta y is given by this, and we write this delta y as f of c plus delta x minus f of c, and we can approximate when this delta x is very small by f prime of c delta x. That's where the formula is given down. Now for such approximations, we call delta x as the differential of x, and we denote it by dx. Similarly, the expression f prime of x dx is denoted by dy and is called the differential of y. Now let's go ahead and give a proper definition to these differentials. So if you're given a function f of x, which is differentiable in any open interval containing x, we denote the differential of x by dx, and it is an independent variable that may take on any real value. The differential of y is given by dy, and this is the definition of dy as f prime of x dx. Now, many applications, the differential of y can be used as an approximation to the change in y. That is, this is the change in y is approximated by the differential in y. Now remember, dy is given as f prime of x dx. So hence this change in y, which is we're calling delta y, remember this is called the change in y, guys. Can be approximated as f prime of x dx, which is nothing but dy by our definition. Let's do some examples. Now, the first example we're going to do is just practice finding these dy's, applying the formula. It is basically a practice of our differentials. So if my y is given to be square root of 9 minus x squared, how will we write by the differential of y? As taking the differential of this y. Now remember, your f of x is given to be square root 9 minus x squared, which is basically 9 minus x squared half. So if I want to take the differential, you're going to be applying the chain rule, which is half times 9 minus x squared to the power minus half times the differential of 9 minus x squared. So what do we get? Half 9 minus x squared to the power negative half times minus 2x, which we can write as half times 1 over square root 9 minus x squared times minus 2x. Now notice this 2 and this 2 gets cancelled, and we will get minus x over square root 9 minus x squared. Okay, this is, guys, just what we have written over here. Okay, now let's look at another example. Y equals x times cosine x. Now this is, to find the differential, is basically applying the product rule. So we take the differential first of x, which gives us cosine x, and then we take the differential of cosine, keeping the x as it is, which is going to be negative sine x. So the dy for this function is given by cosine x minus x times sine x, the whole under parenthesis, times dx. Okay, now let's do more examples, and specifically we will see how different, what is the relationship between, the differential of y and delta y, which is a change in y in this example. Let's take a simple example, fx to be x cubed, and x is defined to be 2 and dx is given to be 0.1. So if I find the differential of y, which is given by f prime of x dx, then just simply differentiate f prime of x, which comes out to be 3x squared. Sorry, differentiate fx, which comes out to be 3x squared dx. And when you just substitute the values for x to be 2 and dx to be 0.1, we get the answer for this dy to be 1.2. Now, this is just a differential of y. Now, remember that we would like to find what the delta y is, and also the derivative's value, remember, gives us the slope. And if you think of dx as a change in x, then this dy represents the corresponding change in y along the tangent line at C. Now let's find the value for change in y, delta y. Again, for the same problem, fx is x cubed, x is 2, and dx is 0.1. Now we know the formula for change in y is given by f of x plus delta x minus f of x. When you plug in the values, f of x, now remember, delta x is nothing but dx. So f of 2 plus 0.1, which is f of 2.1 minus f of 2, which gives us 9.261 minus 8, which gives us 1.261. Now notice that delta y is 1.261 and dy is 1.2. Let's look at this one. dy was 1.2 and this change in y is 1.261. Notice we are approximating the delta y by dy, and the answer is the difference is very, very small. So very important fact we see here is that as this change in x becomes very, very small, the change in y comes very, very close to the differential of y. One more concept we're going to do in this section is calculating differentials. Now we can use differentials to approximate function values. For this, we have this formula which is given by f of x plus delta x, which is approximated by f of x plus dy, which is equal to f of x plus f prime of x d of x. So let's take an example. We're going to approximate the value for square root of 16.5 using the formula we just looked at. Now here, the function fx is square root of x. So if I want to find f of x plus, now remember this delta x is a little small change. We are approximating by fx plus f prime of x dx. Let's replace fx by square root of x. Now f prime of x. Now remember, what's your f prime of x? F prime of x, given your fx, is square root of x. is 1 over 2 square root of x. And when we plug in these values, we get root of x plus half times 1 over square root of x dx. Now remember these values, because we're finding to approximate 16.5. So your fx is basically your fx here. We're going to look for x to be 16 and dx, which is the change in x, which is 0.5. So your fx plus delta x is square root 16.5. And then when we plug in the values over here, so this one is going to be, remember, x is 16, this is square root of 16 plus 1 over 2 square root of 16, dx is 0.5, which is here. Keep in mind once again that dx is nothing but the same as change in x. And after that, we're just plugging in the values. So we get square root of 16 plus half times 1 over square root 16 times 0.5. And when we solve it, we get 4 plus 1 over 8 times half, which is 4.0625. So square root of 16.5 is 4.0625. It's the same when you plug in the number in your calculators, you will almost get the same answer. Thank you. See you later.